My dear students of class 1 medical, non-medical, respected teachers, dear friends. Today I am going to discuss a very important topic, Carnot's cycle, also known as ideal heat engine. Now, first of all, what are the main parts of this Carnot cycle? It consists of number 1, a cylinder fitted with perfectly non-connecting walls and perfectly connecting bottom, and a frictionless piston which is free to move up and down, placed on an insulating stand containing 1 mole of an ideal gas at initial pressure P1, volume V1, temperature T1. Why it is placed on insulating stand? So that when cylinder lies on the insulating stand, it makes perfectly non-conducting from the surrounding. Gas becomes perfectly non-conducting from the surrounding. Neither heat is allowed to enter or leave the system, so that adiabatic process may occur. And then there is a source held at T1 Kelvin. Source is a large reservoir of heat, so that its temperature doesn't change when small amount of heat is taken from the source. समुद्र जो एक गिलास पानी बाहर काढ़ लिए, समुद्र ਨੂੰ कोई फर्क नहीं पैंदा. Like that, because we are taking ideal conditions. Sink is held at T2 Kelvin. It is another large reservoir of heat, so that its temperature doesn't change when small amount of heat is given to the sink. समुद्र ते गिलास पानी पा दिए तो समुद्र ਨੂੰ कोई फर्क नहीं पैंदा. But T2 is less than T1 always. Now, the working of this Carnot cycle or ideal reversible heat engine depends upon the 4 factors, 4 processes. So, first process is known as isothermal expansion. So, first of all, this cylinder is placed on the source held at T1 Kelvin, and the gas is allowed to expand isothermally, slowly, from initial volume V1 to volume V2 say. Then temperature, volume of the gas will increase, temperature of the gas will tend to decrease. But as it is in thermal contact with the source, which is also held at T1 Kelvin, so that temperature of the gas remains constant. So this is the case of isothermal expansion from volume V1 to V2, or we can say from position A to B. So if you plot PV diagram, a graph between P and V, taking volume along x-axis and pressure along y-axis, we get the graph curve AB from A to B, P1, V1, B at B, pressure is P2, volume V2. So this A to B, this curve represents the PV diagram for isothermal expansion. Now, as it is in thermal contact with the surrounding, so heat flows from the source into the cylinder, so that temperature is kept constant, which is T1. So in this case, there is no change in temperature, there is no change in internal energy. So therefore, amount of heat supplied to the gas from the source is equal to the amount of work done by the gas during this expansion. So Q1 is equal to W1, and is given by integral PdV limits V1 to V2, and this we have proved. Work done during isothermal expansion, we can use direct relation. Q1 is equal to W1 is equal to RT1 log V2 upon V1 to the base E natural log. So this is number 1. Also, geometrically, work done will be equal to the area under this curve AB, that is area ABM KA. Area under this isothermal AB automatically is equal to work done, because pressure into volume as units of work. So during isothermal expansion, we have proved that amount of heat supplied to the gas from the source or amount of heat taken from source Q1 is equal to work done by the gas is equal to RT1 log V2 upon V1. Say this is number 1. Now after this isothermal expansion, cylinder is placed on the sitting stand so that bottom becomes non-connecting, and the gas is further allowed to expand from volume V2 to V3, from B to C, from pressure P2 volume V2 to pressure P3 volume V3. And since it is a case of adiabatic expansion, so when gas further expanded, volume increases, temperature falls, because it is thermally isolated from the surroundings. So this is a case of adiabatic expansion. So therefore, we get curve BC and temperature falls from T1 to T2C. And therefore, work done during this process is given by W2 is equal to integral. We go from V2 to V3, P dV, V2 to V3, P dV. And it can be proved CV into T1 minus T2 is equal to area under this adiabatic BC, that is BCNMB. This area will be mathematically equal to work done during adiabatic expansion. So W2 is equal to CV T1 minus T2, and CV is equal to molar specific constant volume. So this is number 2. Now after this adiabatic expansion, the cylinder is allowed to or brought in touch with the sink, which is held at T2 Kelvin, and the gas is now compressed from volume V3 to V4. When gas is compressed, volume decreases, temperature of the gas will tend to rise, but as it is in thermal contact with the sink, which is also held at T2 Kelvin, so heat flows from the gas into the sink so that temperature is again kept constant, that is T2 Kelvin. So therefore, this is the case of isothermal compression. And in isothermal compression, we get the curve CD, and system goes from P3 V3 to P4 V4, and the area under this curve CD, that is CNLDC, is equal to amount of work done upon the gas. In this case, this is the case of, it should be negative, the case of isothermal compression. So during isothermal compression, that is from C to D, let Q2 is amount of heat rejected to the sink. So Q2 must be equal to W3, because again temperature is kept constant, which is T2 Kelvin, no change in internal energy. So the amount of heat rejected will be equal to amount of work done upon the gas. So Q2 is equal to W3 is equal to minus V3 to V4 PdV, because it is negative. So therefore it will be minus RT log upper limit V4 upon V3. If we absorb this minus sign, so we get W3 is equal to Q2 RT2 log V3 upon V4 to the base E, and is equal to area under this curve. So this is number 3. Then after this isothermal compression, cylinder is again brought in contact with the insulating stand to complete the cycle, and the gas is further compressed from volume V4 to V1, that is from D to A, initial volume, to complete the full cycle from A to B, then B to C, then C to D, then D to A again. And in this process, again volume decreases, but it is in thermal contact, thermally isolated from the surroundings. So this is the case of adiabatic compression. So when it is placed on insulating stand and the gas is compressed from volume V4 to V1. So this is a case of adiabatic compression. So temperature will rise, from T2 to T1 again. So this cycle is completed, and the work done will be area under this curve AD, that is ADLAA, this area, and work done W4 is given by from B to A, PdV, we go from V4 to V1, find the volume V1, but negative sign because work is done upon the gas, upon the system. It will be CV, T1 minus T2 again, can be proved. So area DLKAD. So this is work done during adiabatic compression. So we have completed 4 processes: isothermal expansion, adiabatic expansion, isothermal compression, then adiabatic compression. Then the net work done during the complete cycle. This process is repeated again and again. So during the complete cycle, Carnot cycle, W must be equal to W1 plus W2 minus W3 minus W4, because work done upon the gas is taken as negative. But W2 and W4 are equal. W2 work done during adiabatic expansion is equal to work done during adiabatic compression. So they cancel each other. The net work done during Carnot cycle is given by W is equal to W1 minus W3. सबसे value W1 and W3 we have W is equal to RT1 log V2 upon V1 minus RT2 log V3 upon V4. Proved. Now, by some mathematics it can be proved. You can take it directly. V2 upon V1 is equal to V3 upon V4. It can be proved. So therefore, W is equal to R log V2 upon V1 can be taken as R log V2 upon V1 can be taken as common. So V2 upon V1 is equal to V3 upon V4. So into RT1 minus T2. Now, this is the net work done during Carnot cycle. Now, to find efficiency of Carnot cycle. So efficiency of Carnot cycle is defined as the net work done during the complete cycle and the ratio of net work done during the process, the complete cycle, to the amount of heat added to the system. They are taken from the source. So the amount of heat used. So it will be R log V2 upon V1 T1 minus T2 R T1 log V2 upon V1. Log V2 upon V1 cancels, RR cancels. So we get eta is equal to T1 minus T2 upon T1 or 1 minus T2 upon T2, which is required expression for efficiency of Carnot cycle. Eta is equal to T1 minus T2 upon T1, 1 minus T2 upon T1. Very, very important expression for efficiency of. In this way, we can explain the working of Carnot cycle, and hence we can drive expression for efficiency of Carnot cycle. And from this equation, we conclude number 1. Efficiency of Carnot cycle depends only upon temperature of source and temperature of sink. It means it is independent of nature of the working substance. Third point, right hand side is always less than 1 because T2 upon T1 is positive. Therefore, efficiency of Carnot cycle is always less than 1, that is less than 100%. In other words, efficiency of Carnot cycle can never be 100%, because the efficiency to be 100%, either T2 should be 0 or T1 should be infinity, which is impossible. We have taken T1 and T2 large reservoir of heat, but T2 is less than T1. Neither T2 is 0 nor T1 is infinity, so efficiency can never be 100%. It means ideal reversible heat engine or Carnot cycle can never have efficiency is equal to 100%. It means any other heat engine will never have efficiency equal to 1 or 100%. So efficiency of heat engine is always less than 1, less than 100%. Okay. For steam engine, efficiency is between 12 to 16% only. For petrol engine, it is up to 20%. For diesel engine, it is up to 40%. So efficiency can never be 100%. So last, when T1 is equal to T2, eta is 0. It means Carnot cycle or Carnot engine can never work, or any heat engine can never work if difference between source and sink temperature is 0. So sink and source should always be at different temperature. So this is all about Carnot cycle and its efficiency. So till next video, all the best, be happy, good luck, ਜਿਉਂਦੇ ਰਹੋ।